Hello, my name is Chin, and I'm representing the Amazon Recognition team to present our CVPR 24 paper, Learning for Transductive Threshold Calibration in Open World Recognition. Our work is primarily related to open world recognition, which uses deep metric learning to learn to transform raw data into vectorized representations, whose distances between the representations reflect the semantic similarities. During testing, the learned model is applied to unseen open-world classes which are not encountered during training, with the expectation that similar items still remain close to each other while dissimilar items will be kept apart. A key challenge with open-world recognition is selecting an effective distance threshold at test time to determine if two unseen images belong to the same open-world concept or not. This task, termed as open world threshold calibration, involves balancing the trade-off between the true positive rate and the true negative rate for test data, while accounting for the possible distribution shift and uncertainties in the open world. Take optimizing for specificity as an example. This can be formulated as maximizing TNR under a minimum requirement for TPR, as shown in the equation here. Traditional calibration methods such as plot scaling generally underperform in the open world scenario. This is because these methods are typically inductive, relying on calibration dataset to learn general calibration rules under the assumption of identically distributed data. This assumption fails in open world scenarios, where the test distribution is unknown and dynamic. To overcome this, we propose transductive threshold calibration, or TTC, where the TPR and TNR estimations are directly based on the test data, rather than relying on a separate calibration dataset that may not accurately represent the test data. To enable TTC, we designed OpenGCN, a GN-based post-hoc calibration model. OpenGCN integrates TTC by utilizing a GNN to predict the pairwise connectivity probability. These predictions are paired with a threshold to generate pseudo-labels, which are then used to estimate TPR and TNR for the test data at each distance threshold. Additionally, we adopt a unique two-stage training strategy where we pre-train OpenGCN on a large collection of closed examples, followed by fine-tuning on a small open-world calibration dataset containing disjoint classes to the test data to adapt the pre-trained model to open-world scenarios. We conduct experiments on public open-world recognition benchmarks, including iNaturalist, CUP, and CARS. In this scenario, the calibration dataset and the test dataset are randomly split from the same data source, and they're expected to have similar distance distributions. For evaluation, we report absolute errors in TPR, TNR, and multiple target values. As shown in the table, on average, OpenGCN achieves the highest rank across all benchmarks. To assess the robustness of our method under distribution shift, we perturb the test data of the same disk scenario with 13 common corruption types, including noise, blur, weather, and digital distortions. We report the global error metric, which is a combined mean absolute error for both TPR and TNR for each corruption type. As shown, OpenGCN consistently outperformed the baseline methods across all corruption types, achieving an average error reduction of 55% compared to the best baseline. We also consider a more challenging scenario with significant distribution shift. Specifically, we consider calibrating for the long-tail classes as well as cross-domain calibration. As observed in this scenario, all calibration methods display elevated errors compared to the same disk and shift disk scenarios. However, OpenGCN demonstrates superior performance compared to the baseline methods in both OOD settings and the long-tail calibration setting, achieving an average relative error reduction in the global error of 44%. Finally, we summarize the key takeaways of our paper. We formally define the open world threshold calibration problem, identifying key challenges associated with the task. We introduced OpenGCN to enable transductive threshold calibration via GNN, which does not rely on the assumption of matching distributions between the calibration dataset and the test dataset. The evaluation results underscore OpenGCN's effectiveness across different distribution shifting patterns and demonstrating its practical applicability in open world recognition settings. However, compared to traditional calibration methods, OpenGCN is less efficient and more susceptible to overparameterization. Furthermore, OpenGCN is not a calibration data-free method, as it still requires some calibration data in addition to the closed-world examples used for training the embedding model. For more details, please check out our paper. Thank you for your attention.